Good day, class. I hope the past weeks of the course have been fun and you have enjoyed your time as much as I have. For my case study, I decided to research and discuss the various methods, resources, and outputs related to aircraft optimization. This is the topic that I am highly passionate about given the extensive savings and benefits it has to both commercial and military organizations. For this brief presentation, I'll follow the standard outline for the case study. I'll discuss the general problem that was researched, the significance of the problem, the various mitigating solutions I researched, and finally provide a recommendation to the problem. Aircraft maintenance management is highly complex with numerous interwoven processes and outputs needing to come together at the right time to produce an airworthy aeronautical product. An aviation maintenance manager utilizes what subset of information is available to prioritize cost, schedule, availability, and resource management. The overarching system's complexity is such that no one individual has all the information at one given time to prioritize and optimize decision making. The lack of information results in suboptimal output laden with inefficiencies and ineffectiveness. While a maintenance organization should not be cutting corners to prioritize availability and reduce costs, this does happen and the resultant safety of the aeronautical product is jeopardized. With such an extensive network of internal and external organizations and interdependent processes, how does an aviation maintenance manager optimize the delivery of an aeronautical product? Generally speaking, aviation maintenance, as implemented today, is not optimized. It represents a person's values in the decision-making process that are not inclusive of all considerations. This is generally not a fault of the maintenance manager, but an inability to obtain and process all the available information. The net of aircraft maintenance is just too vast and complex. Thus, the end-state solution only considers a subset of information, potentially only in the present and not thinking about what could happen in the near future. This drives a need, desire, and benefit to optimize the maintenance considering and forecasting what information has been lost. The aviation system as a whole and what resources and systems are required to return an aircraft to a serviceable state following maintenance is vast and complex. The interrelations of the various systems, compounding factors such as resource limitations and unpredictability, make the process and program efficiency gains for managers demanding and taxing. By not addressing the scope and complexity of the maintenance event, airlines and militaries run the risk of a decrease in aircraft availability, increase in operating cost, increase in the use of resources, and reduction of profits for the airline and budgetary overruns for the military. A large number of tasks, both scheduled and unscheduled, combined with the limited resources and ever-changing priorities, have a significant impact on the flow of work to be performed and final output. Planning for the unknown typically results in increased inventory levels and reduced utilization of the aircraft by the airline or the military. During the maintenance event, unscheduled maintenance drives additional overtime for the workforce, urgent demand for resources, and errors in quality necessitating rework jeopardizing the safety of the aircraft. The harmonious integration of availability, serviceability, and sustainability in consideration of operations ensures a high degree of operational readiness. It is therefore essential that organizers balance these components to develop an optimal solution. The need to optimize the various areas that impact the maintenance program is a challenging task. As stated, with a vast and complex net and limited ability to see and process information, managers can only gain efficiencies in some areas. Various tools exist to support managers in their tasks, driving a requirement to attempt to solve this program. The aim is to develop strategies and optimization plans for the following critical areas: personnel management, preventative maintenance program, supply chain management, corrective to predictive maintenance program, operations management, structural integrity program management, and the utilization of technology. Forecasted maintenance requirements. The method permits an organization to develop a unique model for their specific fleet by extracting requirements for a maintenance program. The intent is to forecast the workforce requirements for maintenance in a given period with the current support within the organization and what is predicted for the future. By overlaying the available workforce to the model and applying some general constraints and assumptions, the model can optimize the applicable shift, schedule, and resource allocation. For optimized skill sets, the mathematical model optimizes the crew combination, shift sizes, and start times for aviation line maintenance. The end state model offers an optimal solution with varying start times, the number of shifts, and personnel per shift for a given organization size. Reducing stressors and creating a balanced, surge-free schedule is important. The forecasted solution utilizes the previous methods balanced against safety to ensure a reduction in fatigue and a balancing of the maintenance program. The proposed mathematical model that optimizes the final crew schedule taking these factors into account. The fatigue model proposed analyzes data over a given duration of work to determine what a maximum crew day should be, the number of consecutive shifts, and solves a matrix of this information against available crew size and composition. The model predicts a 15% decrease in overall fatigue for the same end state hours worked in a given month for the model chosen. The three models can support a maintenance manager in determination of crew size, schedule, composition, with an end state reduction in fatigue. The three mathematicals provide synergy in helping the organization on how best to employ its personnel. Preventive maintenance program management. Schedule optimization looks at the complete preventative maintenance package, A checks through D checks, and examines the interval of maintenance based on reliability data. Changes can be made to eliminate one of the checks and reduce the scope of a check. The advantages are an increase in the aircraft availability by doing checks less frequently and reducing costs by conducting fewer checks over the life of the aircraft. By optimizing the schedule, the overall scope of maintenance being conducted is decreased over the life of the airframe. Task rationalization refers to reviewing the scheduled maintenance event and ensuring a stable and logical flow of work. Each task is clarified with additional information and limitations to remove any vague statements such as inspect. The more streamlined flow of functions reduces the total task time and scheduled maintenance event by permitting the MRO to plan the required resources and reduce any engineering time needed to clarify the maintenance program. The complexity of the task could be reviewed as increasing if two subtasks are grouped as one, or if the additional information requires an extra step. However, in general, the entire maintenance event is reduced. Predictive maintenance strategies, preemptively removal of components, and health monitoring software solutions aim to improve overall aircraft availability and reduce cost. The benefit of this approach is conducting concurrent maintenance while the aircraft is already unserviceable. However, it comes at the cost of sending a part to R&O earlier than expected to impact available supply management and forecasted costs. The cost-benefit analysis justifies such actions, but is highly dependent on the part, operation, and schedule. The final programming model and the associated algorithm was verified against data from a European airline. For the fleet investigated, the model demonstrated a reduction in the number of checks by 7% over 4 years, saving between $1.1 and $3.4 million in maintenance costs for a fleet of 40 aircraft and $9.8 million in revenue due to the increased availability. To determine what parts are needed, various models are available. The premise is to utilize past historical data to assess future usage, or reliability data to predict future usage. While both have their strengths and weaknesses, the best approach is to use a hybrid model that merges the data to determine an optimal value. The final solution proposed was able to demonstrate a significant increase in the ability to determine appropriate resource requirements. To achieve such significant increases, the ability to determine what parts are required requires an organization to provide information to its suppliers and OEMs. The need to provide information to suppliers and OEMs permits them to best forecast what demand may be in the future. This level of communication allows these organizations to take the lead on inventory levels to prepare for increased or decreased demand. Compared to varying frequencies between daily, weekly, monthly, and quarterly, those organizations that were able to provide daily information saw on-time delivery rates over 95% of the time versus 88.75%. The final component of the proposed solution aims to maintain appropriate in-house stock levels and logistic needs, taking into account the previous information. A resultant strategy of plan for every part attempts to optimize the solution to ensure availability when needed through the informed decision making on parts and logistics management. By balancing the costs of transportation along those of inventory costs, a warehouse can determine the minimal levels of expenses and subsequently optimize inventory levels. The proposed solution is a Kanban inventory control system. Utilizing the Porsche consulting strategy and the optimization mentioned above has been shown to demonstrate a significant benefit to over 50 different aviation companies around the world. Together, it has resulted in a decrease in the overall transportation costs by 30 to 50%, a 20% reduction in part order demand requests, a 20% reduction in stock levels, and 10% increase in aircraft availability. For a scheduled maintenance event, the strategy reviews the entire preventive maintenance program as a series of optimized tasks. As an unforecasted maintenance event is created based on sensor data predicting its failure, the follow-on workload is readjusted to account for this event and optimized to minimize total downtime. The system also permits the unforecasted task to be scheduled at a later date that is optimized for the program. The service deployed by Lockheed Martin can directly improve flight line fault diagnostic by analyzing the fault against previous corrective actions. The machine learning approach compares all sensors data and the aircraft to assist in the accuracy of repair actions to be completed. The system compares previous repairs and recommends a solution based on the probability of success. Cost-effective fleet management is a unique subset of the SaaS solution. Taking sensor data and flight line profiles from aircraft systems, the solution can provide a forecasted maintenance requirement 1 week, 1 month, or 6 months out. The solution is driven towards forecasted operational deployments where an aircraft may be away from its main operating base for an extended period. It provides a forecasting requirement of spares that may be required to send now, hold in reserve, or replace on aircraft as noted above. The study demonstrated with the Royal Air Force, SAS, and Lockheed Martin that the predictive maintenance strategy and business analytics tool can increase overall aircraft availability by 1.06% and save an estimated 1,400 hours of maintenance downtime over the 3 months scheduled. Crew scheduling and operations management. The approach utilized was a modified version of the accelerated Bender's decomposition method, which optimized aircrew scheduling, operations, and maintenance routing. The model, similar to that of personnel management described above, attempts to decompose the various missions, crew requirements, and maintenance requirements. In this manner, an aircraft, aircrew currency requirements, mission capabilities, and maintenance requirements all overlay one another to determine the best fit. Operations and maintenance planning focus on the flight planning process of availability, serviceability, and sustainability. The process aims to introduce better proactive planning than the reactive approach to day-to-day mission and labor allocation. Given a mission requirement, which aircraft is best to be chosen? The flight and maintenance planning optimization model proposed calculated an increase in scheduled sustainability between 18 to 22% and a reduction in maintenance bandwidth by 23 to 32%, depending on various assumptions. All other factors being equal, the simple ability to communicate requirements and optimize aircraft usage to a bed-fist result in a no-cost increase in operational ability. From a military perspective, more so than a commercial airline, the need to manage the aircraft's structural lives is necessary to maximize the experience of an individual aircraft and the life of the fleet. Failure to manage structural lives correctly can result in a decrease in aircraft availability due to the unmanaged structural inspections not calling at optimized times. The end-state solution needs to account for what aircraft should be picked for a given mission based on a forecasted mission profile that maximizes the life of the aircraft and the fleet. This is the problem solved by the United States Navy and the processing modeling company ProModel with their Naval Synchronization Tool. Utilizing real-time F-18 fleet data, it can calculate the best fit aircraft for a given mission, a future squadron's role, what aircraft should be deployed, and ultimately maximize the life of the fleet. The solution was able to provide the United States Navy with an easy ability to source aircraft to the various units, fleets, give visibility into scheduling requirements, assist in operational planning, demonstrate shortfalls in operational capabilities, and increase overall operational availability. Technology is demonstrated as the key to the success of any of these methodologies. The need to outfit aircraft with appropriate sensors and develop or implement software solutions is necessary to perform these strategies. The rationale is that the complexity of the dependencies is far too complicated for anyone to calculate and reproduce. The ability to implement an appropriate model allows an organization to test future ideas, allowing for an evaluation of their impact before being implemented, as well as monitor those that are implemented to gauge effectiveness in the future. The need for an enterprise resource planning solution that interacts across all streams is ideal. Still, ultimately, it is the system dynamic approach to maintenance that needs to be implemented regardless of the end-state software chosen. The problem that was to be addressed is, given the complexity of aviation maintenance, how does a maintenance manager optimize the delivery of an aeronautical product? The above recommendations serve as options for a maintenance manager to consider and to establish a follow-on business case for their organization. Not all solutions would need to be implemented in every organization, as some users already have conducted their business case and options analysis. That said, the options provided are aimed to give some insight into the benefits that could be gained by implementing these solutions that could warrant additional research. For example, the United States Navy solution for the Naval Synchronization Tool may justify an easy business case for a military organization to optimize the structural life of any aircraft, but not apply to commercial organizations. Simply put, it is a shopping list of ideas for organizations to choose from. In conclusion, how does a maintenance manager optimize maintenance on their fleet? Well, it depends. The question is, where does the maintenance manager want to start, or what problem do they want to address first? The options discussed are estimated to save some organizations around $20 million in operation and maintenance costs, increase availability by 1%, save over 1,400 man-hours of maintenance, double the ability to predict parts failures, optimize task sequence to return an aircraft out of a heavy check faster, and various others. For an organization not doing anything today, the options discussed provide numerous savings aimed at increasing the end-state operational output, availability, and success of the organization. The options simply provide research on what has been conducted by other organizations to date and insight into the various solutions that are available. The implementation of any solution in an organization will vary, but they are a stepping stone to what is achievable given the implementation of the appropriate technological solution. Thank you.